Het Schouten heeft 2,5 jaar lang in Duitsland bij Google gewerkt. Hij is inmiddels al wel enige tijd terug in Nederland. Is allerlei spannende dingen aan het maken gegaan, omdat hij daar geïnspireerd raakte door de manier hoe ze daar werkten. Spreek ik het goed uit wanneer ik CloudABI zeg?
Ja, perfect.
CloudABI is super cool, hij gaat er dadelijk allemaal dingen over vertellen. Het is iets wat hij momenteel helemaal in zijn eentje volgens mij aan het maken is. En ik snap echt nog niet waarom Bright hier niet in de zaal zit. Want het is een super hippe start-up. De spannendste talk van vandaag, wat mij betreft. Het Schouten aan jouw woord.
Okay, now hartelijk dank. So I'm going to give this talk in English. There are a couple of people in the audience who are visiting from abroad, so that's why I prepared all the slides in English as well. So, as Peter Paul mentioned, I'm going to talk about CloudABI today, which is a piece of software that I've been developing for the last half year. So, this is being developed by my own company that I founded as well, called NLUUG VJ15. It's just Unix with some byte ordering issues. And all of this is what I've developed so far is open source. There will be some commercial tooling built around this in the long run. My company also provides commercial support on this piece of software. So I really I'm looking forward to hearing your opinions, what you think about this. It's the first time I'm actually talking at a conference about this. It's the second time I'm actually giving a talk about this. Before I'm going to explain what CloudABI is, I'm first going to explain what is wrong with Unix in my opinion. The reason why I'm not explaining what CloudABI is in the beginning is that if I would just explain to you what it is, it would actually be without a context and it would be really hard to understand why you would want to use a piece of software like this. After explaining what CloudABI is, I'm going to discuss a couple of use cases, how you could use this to actually run software safely and securely at a large scale. So Unix systems are really awesome. I'm not really old, I'm only 29 years old, but for the last almost decade, I've been, or more than a decade now, I've been using Unix-based operating systems. I'm really enjoying using them. They're really nice, but they get a couple of things wrong. So first of all, they don't really help you to run software securely. I'm going to explain more about that in a minute. And second of all, they make it really hard to actually test software and reuse software, which I'm also going to show you in a minute. So the last thing, that systems administration on Unix systems doesn't scale. I'm not going to explain this right now, but I'm going to save that to the end of the talk, where I'm going to look at the use cases. So the Unix classical security model is actually quite simple. Processes, they have credentials. A process has a user ID it's running as, it has a group ID, it even has a set of groups that it's running as. It also has an effective and a real user ID, and there's a whole bunch of user IDs and group IDs, and people most of the time understand how they work. A lot of objects on the system, so I'm talking about files in the file system, but also semaphores and some other things, they have access control lists. And most of the times these access controls, they're just as traditional Unix access controls. You have an owner and a group and some permission bits. These credentials and access controls are most of the times rather static. You start up a service on a Unix system and it simply has those credentials, and after it has started, those credentials rarely evolve. The same holds for the access controls. You can change multiple files on disk, but most of the times they're just constant. There are some parts of the system that simply don't have any access controls on them. So, for example, creating a network socket and making an outgoing network connection to some random IP address on the internet. There's nothing you can change mod or change own to actually restrict this. Over time, you've seen that these rather complex systems have started to appear that allow you to tune these, but most of the times these systems are really hard to understand, or they're operating system dependent. So my observation is that the traditional Unix security model is really good at what it was designed for, namely interactive logins on a multi-user system. You log in as user add, type in your password, you get a shell, and of course you want to run all your processes as user add. And the access controls on disk have to match against that user. You want to run an editor and a compiler or an IRC client, and the permissions on the file system it's quite a good model. In my opinion, it's a pretty bad model actually for running services. If you're running you maintain a server for your company, you have to run your web server under a certain user, but it doesn't really make sense. You come up with all these sort of fictive user accounts for non-existent people to run your services as. And I'll demonstrate to you that this is actually really bad practice and really, provides bad security. And there are a couple of examples I can think of that are even worse, but the most canonical example I can think of is running a web service. Everyone runs web services nowadays, so I thought it was a good example. So this web service would only need to access a couple of resources, handful of resources. There are incoming HTTP requests that this web server would need to answer. It then takes a look at the HTTP request, extracts the path name that's being requested. Depending on that, it opens a file on disk. So there's somewhere a directory in the system storing all the files that need to be served. You might have more complex web applications. A PHP script in there would be a good example that opens a connection to a MySQL database. So it would need to access a couple of database backends. Typically not that many, it's just a handful of database backends. But in practice, this web service can do a lot more on the system. If there's a security bug in this web service, an attacker could actually create a tarball of the entire system and send it to a remote location. You really have to make sure that all the file system permissions on disk are all right to make sure that an attacker can't just run away with all your data. So after this web server is exploited, you actually kill the web server process because an attacker did something bad to it. It restarts, you've patched it up, no more security bug, but in the meantime this attacker could have installed cron jobs in the system, under the user of the web server. And every couple of hours it starts up a new backdoor that the attacker can log into. That's pretty bad. So now you're trying to stop that. You're trying to log into the system and actually prevent that from happening again. But in the meantime, the attacker is smart. He's running a script in a for loop to actually run the write command and spam your TTY. So as a systems administrator, you can't do a lot. You have to know this command called message, run message n, and then it stops, but you have to know that it exists. It can also turn the system into a botnet node. It can run a process that opens like 1 trillion TCP connections open to this random website on the internet and can just pull it down entirely. And that's stuff that a web service shouldn't do. So the only thing a web service needs to do is handle incoming network requests, send a response. In practice, it can do a lot more. And I personally think that's really bad. To go back to this slide, another awful example I always bring up is Tcp Dump. That's also a really good demonstration of insecure software in Unix. So you run this command as root, and it actually parses network packets. It has tons of parsers in it. There's one security bug in one of those parsers, and an attacker could send a malicious packet over the network that you sniff and actually run code on your system, running as root. So Unix the Unix security model is good for interactive logins, but for services and administrative tools, it's really bad. So, in my opinion, software in Unix is also really poorly reusable and testable. And I thought about how to explain this. I was trying to come up with examples showing you why Unix software isn't really testable. But eventually I decided to go on a different route. Instead of taking a look at Unix software, let's take a look at Java. So assume we want to write a web server in Java. You're an amateur Java programmer, you just learned how to write Java code. And the first thing you do is you write this class. It's an incomplete class, of course. There needs to be more logic in it, otherwise it wouldn't actually serve stuff over the web. But it actually has a global state consisting of a networking socket on which requests come in, and it has a root directory that stores the files that you want to serve over the web. So if you want to construct such a web server object, you could, for example, first create a TCP socket, let it bind on port 80, and the root directory needs to be var . This class is, of course, not really reusable and not really testable. Why isn't this class reusable? Well, it assumes that you want to run the web server from port 80. You can't run this web server twice. It's also not reusable because it hard-codes the path. It's also not testable for this reason, because you can't just spawn this web server twice on the system. You know, you make an updated version of the web server, you want to test whether it works. Spawn the second one, it will just complain that the TCP port's already used. So what do? You extend it. So this would be the most obvious way to extend this class. You know, add a port number parameter to the constructor and add a path name that you want to use as the web server root directory. This is already a lot better. But actually, if you've done a lot of Java programming, you would actually write something else. You would namely write this. Instead of letting the caller pass in a port number, you actually let the caller provide the socket. And this is actually a lot more flexible, because this now means that you can just pass in any type of socket that you like. In the previous example, we passed in a TCP socket, for example, but nowadays everyone, or there's a lot of hype around SCTP, which is a sort of a more complex streaming protocol. I don't know all the details. You could also just pass in an SCTP socket. You could even pass in a Unix socket. Another advantage of this model is, instead of passing a string of a path name, we just pass in an interface that provides us file system access. You know, it doesn't need to be an actual file system on disk. You could have a virtual file system in memory of the Java process that stores some files that you want to serve over the web. So this is actually how a decent Java programmer would write this code. And this construct is typically called dependency injection. You inject the dependencies that your class should have into the object, instead of letting the object construct it itself. So now if we take a look at how Unix software typically works. So my observation is parameters are typically hard-coded in applications. A lot of Unix services hard-code certain properties. And if they don't, and allow you to configure it through a config file, they actually hard-code the location of the config file. Also, resources are acquired on behalf of you. You specify in a config file, I want to let this web server run on this IP address and port, and then the web server process opens it on behalf of you. It's not that you provide the socket to the application itself. So it's actually, Unix software is like a badly written Java process. That's basically what it boils down to. So now I'm going to show you a very simple web server process. This actually works. You can just type it over, or maybe get the slides after the presentation and try this out, and it actually works. And what is this? This is just a web server where I've ripped off the initialization part, so to speak. So it happily assumes that if it starts up, that there is a socket already on file descriptor 0, and it can just accept connection from that. So this is just a simple web server that, if you visit it, it just returns hello world in plain text. It doesn't conform to any HTTP standard. I know it's a completely broken web server, but it's good enough for this example. So this web server is actually, even though it's so tiny, it has a couple of really interesting properties that, that some other web servers don't have. So without modifying a single line of code, this web server supports IPv6. It supports IPv4. It supports TCP, it supports SCTP. What does it do more? It can bind on any port number. That's because we provide the socket. The person that launches the web server is responsible for setting up the socket properly and says, here, use this instead. This is where you get the request from. Another very interesting property is, it's actually a concurrent web server. So when you look at this process, it's just single-threaded. It's just a single loop that accepts requests, generates a response, and closes the file descriptor. But the interesting thing is, if I would just create a single socket and spawn a dozen of processes against it, I would suddenly have a concurrent web server without writing a single line of code. This web server is also very easy to test. So for example, if you want to test Apache, you have a configuration, a whole bunch of configuration files for Apache, but you just want to run a testing instance on your workstation. start it up, and then send a couple of requests to it in an automated way, check whether the output is correct, and then shut it down again. The problem is that if you want to do such a thing, you actually always pick a random port number on the system. Random 1, 2, 3, 4, 5. This is actually completely unreliable, because if you would run this test twice at the same time, it would fail, because you can't run the web server twice on a single port. This web server is actually really easy to test. You just create a Unix socket, just add an arbitrary path, start at the web server, send a couple of requests to that Unix socket, and you can test it. So you can see that this tiny web server with code removed is actually more reusable and more testable. All these discussions on the internet about pieces of software that don't support IPv6 yet, in a lot of cases it wouldn't happen if a web server, or if that specific service was written like this, to just assume that you pass it the file descriptor. You can actually do a lot more interesting things with it. So one annoyance is that a lot of services, you can specify the port number it should bind on, but not the IP address. I've seen it in a couple of cases. Instead of patching up all those applications to also allow you to bind on a specific IP address, if you could just provide the file descriptor, that functionality would always be there. So now that I've described what I think is wrong with Unix security and testability and reusability, let me show you what CloudABI is. So CloudABI is a so-called application binary interface. It's, everyone knows the term API, namely it's a set of functions that you can call, a set of classes, just something you can program against. But an API is similar to that, but it's at the binary level. So it really explains conventions. There is this system call, it takes these parameters, they're stored in these registers, and if you do this, then you remove a file from disk. And CloudABI is essentially just a specification for it. It's this really compact binary interface, and it's designed in such a way that it allows you to develop software that is better protected against exploits. It allows you to write software that's easier to test and reuse, and it actually eventually allows you to develop software that's easier to run at a large scale. So, even though I've invested a lot of time in it, and I think there's also quite a lot of innovation in things that I've written, I have to be honest, CloudABI is for a large part based on something called Capsicum. Capsicum is a security framework for FreeBSD that's been developed by a couple of people at the University of Cambridge in England, and that work was funded by Google to actually eventually be used inside of Chrome to make sandboxing in the browser more secure. So, if you start a CloudABI process, just the simplest process you can imagine, it's secure by default. A process that's running on CloudABI can't do a lot of things. It can allocate shared memory, pipes, just memory for general use. It can spawn threads and sub-processes, and it can interact with clocks, and there's a handful of things it can do. Essentially, it can do all the things that are needed to just compute stuff. It is safe to spawn a sub-process, of course. There is no global impact on the system. It does use up some load, but it's not as if you're making a connection to the outside world. It's not like you're removing a file from disk that other processes might be using. It's really self-contained. If you would kill those processes, not a single trace would be left behind, of course. So a couple of things that you can't do by default is open a random path from disk. Open /etc/mine types for my mine types database, a web server. You can't create an outgoing network connection. And you can't just take a look at the process table and say, I'm going to kill this random process that happens to run as the same user. It's really isolated. But of course, this is not sufficient for most programs. Most programs want to do more than just compute things. So rights are granted to the process by just providing it file descriptors. So if you would grant, or if you would start up a process and provide it file descriptors to directories, the process can suddenly access parts of the file system. It can only access parts of the file system underneath that directory. And the nice thing about it is, the process doesn't even know the global path name of the directory. You just give the directory and it doesn't even know where that directory is. So it allows you to just start up a program and just give it different file descriptors to different parts of the file system. And it's completely up to you. You just start up the application, inject all the things into it that you want to provide access to. Another thing that you can do is you can start up the application with sockets. You know, we've seen this before with the web server example. But an interesting use case is that sockets on Unix can also be used to pass file descriptors. So if you have two Unix sockets between two different processes, one process can put a file descriptor into a socket and it pops out on the other side. And this is actually really nice. So processes can give each other rights. They can just donate certain rights that they have to other processes. So file descriptors, they also have these permission bit masks. So normally in Unix you can open a file for reading, you can open a file for writing. But this is clearly not granular enough. So a socket, you can't open a socket for reading, of course. And also the problem is, if you open up a file and duplicate the file descriptor, you can't change the way it was opened. So a huge limitation of Unix would be, you create a piece of shared memory, you get a file descriptor to that, because nowadays in the latest POSIX specification, shared memory objects are also file descriptors. You want to be able to write to that piece of shared memory. But if you pass that file descriptor on to another process, that other process might, you wouldn't want to give write access to that. You know, you can't do that on normal Unix systems. But there's a really simple call called cap write limit that's also part of caps command FreeBSD. And that allows you to just say, I make a copy of this file descriptor. Now on this file descriptor, disallow writes. And then you can pass that piece of shared memory to another process and it can create a read-only mapping. So these permission bits really allow you to make, you know, to tweak apps to make them more secure. So let's take a look at our secure web service, you know, or our simple web server that I wrote a couple of slides back. So assume you would start up this web server and you would give it a couple of file descriptors, namely a socket for incoming HTTP requests, a file descriptor to a directory that contains the web server's root, and an append-only file descriptor to a log file. If there's a security bug in this web server, then the worst thing that an attacker can do is read all the files in the web server root and send them back, which you could normally already do, for example, and append garbage to the log file. So the attacker can't actually remove entries from the log file, it can only write garbage into it, because we have set the permission bits on the logging file descriptor in such a way that you can't seek in it, you can't, you know, truncate the file, you can only append stuff to it. Even funnier, if you would turn off read there on the directory file descriptor, the attacker can't even scan the file system, you know, the directory that you've exposed. It must really guess the file names. And that's, you could argue that that's already the same as what you can normally do over HTTP, right? You know, you just send it GET requests. So in this specific case, there is very little for an attacker to gain if he would exploit this web server. It doesn't really matter. Maybe you could even say that it's a feature, you know, allowing a hacker to just run arbitrary code in your server to just interpret web requests the way he likes. It doesn't really matter. The nice thing about this model is it's not a fixed policy. You know, the traditional Unix permissions and credentials, they are typically fixed. They don't change a lot. But this is actually a flexible model. If you close a file descriptor, you give up that right to access this. And you can actually use this in a lot of creative ways. And on the next two slides, I'm giving a couple of examples of how you could harden software even more in depth. So say this web service allows you to upload videos. It's you know, YouTube 2.0. There's some kind of web form, and you know, person drags a video into it, clicks OK, and the video streams over to your server. It's typically the issue that these video sites, they all want to store these videos internally in a common format. You know, people have all different brands of smartphones and what have you. But eventually you want to be able to stream it to, you know, a device that only supports H.264. So what you do is you already recode it on the server because you don't want to recode the video for every request. So in theory, there could be an exploit in your video decoder or encoder software. You know, the attacker sends you a faulty MPEG stream, and your decoder just goes crazy on it, and suddenly you have an exploit. What you can do in this case is you can just fork your web server. And this sub-process, you only give it 2 file descriptors, namely 1 pipe for the incoming video stream and 1 pipe for the outgoing video stream. Now if there's an exploit in your video transcoding pipeline, the attacker can't do anything special there anymore. You know, you can just write out garbage video output. That's the really nice thing about it. This is really what distinguishes it from all those, you know, the container technology out there. You know, with containers, it's like, I don't trust this whole stack of software, just throw it in one container. But with this, it's dynamic. It's containers in containers, essentially. You know, processes are free to restrict things even more. Another interesting example I could think of is, you don't see this a lot nowadays anymore, but say you're a traditional Unix guy and you operate a web server cluster where everyone has a /tilde directory. So /tilde maps over to home add ... containing all my data. Oh, that's nice. Well, my family wishes me luck for giving my talk. How cute of them. So traditionally those web servers would always have access to the entire file system, right? They would, for every request they get in, they see a /tilde whatever in there. Then they check the password file to figure out your home directory and try to see if there's a web directory in there. That approach is actually quite insecure because it requires the web server to have full access to the file system. But in this specific case, what you can do is you can actually start a separate process. And this separate process has access to the entire file system, or maybe just /home, it doesn't really matter. And for every incoming request that you get, the web service process parses the HTTP request, cuts out the username, and then sends a tiny RPC to this other process saying like, hey, I've got a request coming in for user add. Could you please give me back a file descriptor for home add ... And now the nice thing about this approach is that if there is an exploit in this front-end web process, then that still only means that the attacker can access web directories and not the rest of the file system. So this is really what defense in depth can be used for. And this is really a distinguishing feature, in my opinion, that a lot of the modern container / sandboxing systems lack. AppArmor is a prime example of this, for example. You can only create policies at an application level. So for a web server that can access home directories, you basically have to say, it can access all home directories because it needs to open those directories underneath. And with this, you can actually make a separate process where you put the logic in. And then it's a lot more secure. So testability of CloudABI processes. I've already spoiled this a couple slides ago. Testing of processes is really simple. Just start the processes with different file descriptors. Because you know that processes can't do anything outside of the set of file descriptors that they have. It's impossible for them to just open an arbitrary file in /edc. My observation is that this also makes it a lot easier to migrate processes. Because what you can just do is, for every running process, just take a look around at procfs and take a look at the file descriptors that they have open, and then you know exactly what kind of resources they're using. And then you can just move them over to a different system. So, cross-platform support. A really nice thing about CloudABI is it's so compact, it can easily be added to different operating systems. I'm too lazy to implement an operating system kernel myself. There is no CloudABI OS, but it is really trivial to add it to different operating systems. So a nice thing about this is it actually allows you to run the same binaries in different operating systems without any recompilation whatsoever. You compile an application on FreeBSD, you can just run it on Linux. The other way around, you can even develop on your Mac. So right now, I'm focusing on a single architecture. This is not because I hate other architectures, but it's because I don't have that many other systems at home. So I'm just focusing on x86 64 for now. There are a couple of operating systems that I support. Right now I support FreeBSD and NetBSD entirely. And the reason for this is not that I hate Linux, but next month I'm going to BSDCan, which is a conference really focused on BSD, so I really wanted to be prepared for that. Right now I'm actually working on a Linux board as well. And yesterday I made a breakthrough. It can now run a Hello World program. Yes, other operating systems, I don't think I'm going to add them personally. It really depends on how well used they are. If there's a company that says we're using this different operating system, we would like to run this software on it, here's a contract, I can work for them as a contractor, sure, then I would work on this. But right now I'm just focusing on these operating systems. So CloudABI ships with a C library called CloudLibC. And it's a really, well, I've written it personally, so I would say it's a really awesome C library, but it's 90% POSIX compliant. All of the things that don't work in this model, open, the system call doesn't work because it tries to open a random file on disk. But open@, the POSIX function that allows you to open a file relative to a directory, is implemented. All of the things that don't work with this model are simply left out. And I know this breaks a lot of software. A lot of software uses all these functions that depend on these global namespaces. But one nice thing about leaving them out is you can compile it and you know exactly what needs to be adjusted to work in this model. And this is already a huge improvement over, for example, FreeBSD's Capsicum. Because if you enable Capsicum mode on FreeBSD, that also does something similar, all the system calls that conflict with this model, they fail silently. I've seen one case where a crypto library couldn't open dev random anymore, so it fell back to get time of day and get bit, simply because of this reason. So in my opinion, the build should break. If code doesn't work with global namespaces, it should just break, and you just have to go to your text editor to figure out, like, how should I fix this? A nice thing about this C library is the testing coverage is really high. I'm really aiming for at least 100% testing coverage on a per function basis. And the nice thing about this model is it allows me to test for consistency between operating systems. I was able to port CloudABI to NetBSD in 2.5 weeks just because I had this many unit tests. And I know that all the interfaces simply work. I just kept on iterating until all the tests started to work. So unit tests are really awesome and really make sure that CloudABI works consistently across operating systems. So how to install CloudABI? I'm just going to explain this really briefly because we don't have a lot of minutes left. Just go to GitHub, install a download Clang and Bin utils, install them on your system. Go to GitHub, download CloudLibC and install it. After that, you might want to install a couple of other optional libraries. You might want to have C++ support. And then you can patch up your kernel as well, compile binaries and run them. So now use cases for CloudABI. I'm going to spend the last couple of minutes on this. So at my previous job, we used Google App Engine a lot. Well, I work for Google, so that explains why. App Engine is an awesome service. You just throw a pile of Python code over the fence, and they just run it for you. They scale it up for you. It's really nice. Bye-bye systems administration. The only problem is it only runs Python, Java, or Go code, because they need to run this code safely in a sandbox, an interpreter. With CloudABI, you can actually build a cloud computing service that actually allows you to run arbitrary binaries without requiring any virtualization. There is a lot less CPU overhead compared to Amazon EC2, for example. Another nice use case is, because you inject all these file descriptors into the binaries, you actually know the dependencies of all the programs. You know which other backends they depend on. You know which parts of the file system they use. This would allow you to build a cluster management suite that's a lot more high level than what we see right now. Where, for example, the cluster management suite determines, like, hey, that socket that you've opened or that I've provided to you, you are actually taking quite a lot of time to accept these connections. So I'm just going to start up a second process next to it that also uses the same socket. It allows the cluster management suite to use better locality. It knows all the dependencies between the processes. So it can say, I'm going to run these two processes on the same system or the same rack, because they are strongly connected to each other. And there are a couple of other advantages to this. A final use case would be sort of a native client. Google Native Client allows you to run native binaries inside of a browser, running Quake-free in the browser, essentially. This is already part of Chrome. CloudABI is same as native client, but not tied to the browser. So you could actually automate any program you like. Any program that you have written and you want to add plugin / scripting support, you could just run a CloudABI binary next to it, and you can be pretty sure that it doesn't attempt to leave the system. So yeah, those are a couple of use cases that I foresee for CloudABI. And here on the last slide, I have a couple of links. They're not, well, they're clickable. I'll make sure that I send the slides over to Peter Paul, and then later on, or you can just Google for these terms. If you use CloudABI, it's the first Google hit already. So that's it, basically. Are there any questions?
Questions?
Oh, now Klaas is going to ask a nasty question.
How far are you except writing a new libc? Do you need provisioning infrastructure and stuff like that, and who's going to build that?
Yeah, that's a really good question. So, so to be honest, I haven't just written a libc, it's also all the kernel patches are out there. You know, so far I'm just working on the infrastructure that allows you to run these programs on a bare Unix system. But eventually my hope would be that I can somehow manage to get funding on this, that people think like, hey, this is an awesome concept. We want to do more with this. And writing a cluster management system around this would be awesome, but so far it isn't there yet.
More questions? Otherwise, I have one. Could you tell me your ELF file system story again?
Oh yeah, I think I've told you that for a long time ago. So this is really nice. So CloudABI just uses ELF executables, just like Linux and BSD uses. So in the header of ELF executables, there's a couple of bytes reserved called the OS ABI. And that one indicates, is this a binary for Linux? Is this a binary for Solaris? Linux does a really sloppy job of filling that field in. So all the binaries that are on your Linux system, they're all branded for Solaris, and they magically work. But the idea behind it is if everyone would do this correctly, if you would run a HPUX binary on NetBSD would say like, sorry, this is for HPUX, not for me. So CloudABI uses its own OS ABI number. The problem is, ELF was standardized by SCO, the company that we all love. So SCO no longer really exists. So how am I going to register this number now? So for a very long time, I just used the number 123 in my own implementation, but I thought I should use this. Eventually, I found this old email address, registry@caldera.com, the previous name of SCO even. And I sent an email to that address, like, hey, what does it take to get this number registered? I got a response within, I think, 2 office hours. It was insane. Some guy in the US said, like, yeah, what do you want? Just give us like the company name and that kind of stuff, and we register it for you. So CloudABI is number 17. I am my own operating system vendor.
So that makes a good story.
Yeah, but that they responded so quickly, it was unbelievable. Are there any other questions, by the way? Let's see if you go over there.
Hi. I was wondering if, I mean, you're focusing very much on the cloud, especially with the current name.
Yeah.
But do you have any ideas on using this in a more, desktop-oriented way or something? Because I think some of the ideas could certainly be used to improve the security of not just cloud-based applications.
Yeah, exactly. So the problem with desktop environments is that, say if I want to harden my IRC client, would be a really good example. The problem is that this IRC client would need to interact with this more traditional Unix environment as well. So instead of using CloudABI, I would actually advise people to use Capsicum for now. So that's actually a good mixture, because then you still have the traditional Unix APIs, you set up everything properly, and then at one point in time you just call cap enter, and then it becomes a sandbox process. It's a lot harder to use than CloudABI, but I think for a traditional Unix application that needs to integrate with terminals, read dot files from home directories, all that kind of stuff, it makes a lot more sense for now. There could also be a sort of a more hybrid setup, where the entire IRC core, you know, the thing that makes the outgoing network connections and is most prone to security bugs, would actually run as a CloudABI process that's completely sandboxed, and that you would just have a separate front-end process that uses the ncurse library, and it's just a, you know, standard Linux binary, and that one loads up the dot files for you. So all the traditional Unix stuff, the integration with Unix, so to speak, would be in a Linux/BUC process, and all of the interesting things that, you know, could be exploited, you just run as a CloudABI process. Yeah, I decided to go with the CloudABI name because, you know, I've already shown you a couple of use cases. I really think that especially for large-scale cluster computation, something like this would be really good. So that's why it's called CloudABI. But it doesn't prevent people from running these CloudABI binaries on their workstation. It would be really interesting to see that happen as well.
You mentioned kernel patches, but
yeah.
How invasive are there? Do you support, which kernels do you support? Because that's always the difficult.
So that's a really nice question. It allows me to rant about Linux as well.
Yeah.
So Linux is actually one of the worst operating systems ever to add this to. So what I really like about especially NetBSD is that they, so FreeBSD, NetBSD already support Linux binaries, for example. There is already a subsystem in the kernel that allows you to run binaries of different flavors. On NetBSD, you just say, I want to support ELF binaries that have number 17 as well. Here is a structure with a whole bunch of function pointers, and those are all callbacks that you could just override. And then you just have your entire API just implemented yourself. On Linux, this layer is completely missing. You know, as I mentioned, it even ignores the binary number or the API number right now. It just runs everything. So I'm working on some patches for Linux to also make this a bit more flexible. We'll have to see where this goes. On FreeBSD, the port was the easiest. It required the least amount of effort, especially because FreeBSD already supports Capsicum, so I lean on loft code. NetBSD was the easiest to add to because I really liked how clean the kernel code was, and all the APIs that I needed were already there to get it forward. And yeah, Linux, I'll stop talking about Linux. Nothing good to mention.
Unfortunately, there's no more time left, so I really would like to encourage you to go on with your startup. Have luck. Thank you for your talk.
Yeah, I hope you guys enjoyed the talk, and you know, if you're interested, come talk to me as well here at the Dutch Unix User Group Conference, or send me an email. That's an address you can send emails to, and then I'll typically respond quickly.
Thank you.